name is Mason Giacchetti.
My name is Mitchell Craven.
My name is Sean Flannery.
And we are the contributors on the presentation titled BERT Transformer and Graph Neural Network Application for Top Anti-Top Quark Identification in the CMS Detector. So our group is mainly focused with exploring the fundamental laws of physics, which in regards to the quantum realm are described by what's known as the Standard Model. Now the Standard Model of particle physics simply describes all the fundamental particles as we know them and the interactions between them. Now the Standard Model is actually built up of a bunch of composite theories, so-called quantum field theories, which describe smaller aspects of the Standard Model. Now the quantum field theory that we're interested in is known as quantum chromodynamics, or QCD. And it describes the interaction of quarks with one another via the strong nuclear force. Quarks are the fundamental particles that make up the building blocks of the universe, things such as tables and protons and neutrons that make up the world around us. And one of the predictions made by QCD in particular that we're interested in is what's referred to as toponium. Now, a specific type of quark, a top quark, is very heavy, and toponium is when you have a top quark interact with an anti-top quark, a bound state between these. Now, in theory, this should be impossible because the top quark is so heavy and unstable that it should decay before this is possible. So by identifying it, we could locate flaws with quantum chromodynamics and help to improve and make a more robust perturbation theory out of quantum chromodynamics, better predictions. And the data we'll be using comes from the CMS detector, or the compact muon solenoid, which is one of the detectors on the Large Hadron Collider in Geneva, Switzerland, operated by CERN. The Large Hadron Collider collides protons, which are full of quarks, at high energies, which make a bunch of particles which shower. And because of the high energies, a lot of different events occur that we can observe and measure and detect. So the CMS detector is what we use to acquire our data.
So to search for toponium, we're going to be using a neural network. When you train a neural network, you feed it a training set, and the data from that is passed through a myriad of nodes, each one with its own weights and biases. Every time your neural network makes a prediction and it gets it wrong, it adjusts your weights and biases accordingly to adjust for patterns in your data. You have different kinds of neural networks. For example, graph neural networks are very good at analyzing graphical data. And in our case, it's graphical data based off of the leading order Feynman diagrams. Another type of neural network is a transformer, which is position independent, requires pre-training and fine-tuning. In our case, we're going to be using the BERT model, which was previously used in language to accurately predict words and phrases and sentences. It would be fed sentences with blanks using a position embedder to keep track of the locations of each word and predict which word would fall in those blanks, similarly adjusting its weights and biases based on its accuracy. In our case, instead of filling in the blanks of sentences, we're filling in the blanks of missing particles and detected events. That's our pre-training phase. As we get the same part of each event, the decayed products, as we get the same part of each event, we don't need a position embedder, and thus our model is position independent.
And so our general goal is to find physics discoveries within toponium. And as mentioned before, we're doing this through two different methods, a multi-layered network, which we're developing into a graph neural network, and a transformer that uses BERT. Graph neural networks use data represented as graphs, and we're using predictions from Feynman diagrams, and transformers are performing neutrino reconstruction to find the original particles which they came from. We're going to try to find the best option of the two, and then once we decide which is best for our purposes, we're going to move forward with it. In our neural network performance, this is two graphs from the multi-layered neural network, which we're developing into a graph neural network. The network was previously able to identify CMS data from random background noise, and is now being developed to identify toponium events from general top quark events. The graph on the left shows general loss. We want both the training loss and the validation loss, the orange and blue lines, to go downward. The blue line is, but the orange line is not, so we're going to try to develop that more. And the plot on the right is our separation graph. The tiny orange peeking out is the properly separated data. Our future plans include further developing these two neural networks to the point where they're actively able to identify toponium from TT-bar events.
Thank you very much.